Just 1 minute.
Okay.
Can you talk a little bit just to make a test here?
Okay. Can you hear me? My name is Ali
Yeah.
Övgen.
Yes. Okay. Good. Ok, pessoal. Então agora a gente vai ter aqui a apresentação do professor Ali Gum. O professor Ali é professor da Universidade de Física, né, do Oeste do Mediterrâneo e é um dos grandes especialistas aí em buracos negros, né, em astrofísica de buracos negros. É um grande prazer ter o Ali aqui com a gente hoje, como um dos palestrantes. So today we're going to have the presentation of Professor Ali Gun. He's an associate professor at physics at the Eastern Mediterranean University and one of the main experts in the area of cosmology and black holes and astrophysics with black holes. So it's really a pleasure to have you here with us, Ali. And the stage is yours to make your presentation. Thank you.
Good morning, everyone, and welcome to my presentation. First of all, let me thank organizer of this wonderful conference. 1 minute. Okay, can you see the slides?
Yes, yes, we
Okay,
can.
very good. Okay. So I am Ali Övgen from Eastern Mediterranean University in Cyprus, and today I would like to talk you about the probing black holes with shadow imaging and with deflection angles. And this is very exciting topics in astrophysics. First of all, we start by discussing the shadow cause of black hole, which is a direct manifestation of the event horizon. And I also highlight the recent groundbreaking observation of the shadow of the supermassive black hole in M87 by the Event Horizon Telescope collaboration. Furthermore, after that, I will discuss some constraint on the properties of the black hole that can be inferred from this observation. And then in the other part, I will give a brief overview of the Gibbons-Werner method, which involves using the Gauss-Bonnet theorem to calculate weak deflection angles of light rays by gravitational field. And after that, I will conclude my talk. So black holes are the most extreme gravitational objects that we can expect to exist in the current universe. One of the current frontiers in the black hole research is understanding the strong field dynamics that occurs in their vicinity. Recently, this LIGO-Virgo collaboration has made binary black hole mergers increasingly accessible, and this detection around these 10 such mergers to date to general relativity, and it provides clear expectation for properties of the black holes. And for example, the no-hair and uniqueness theorem predict that black hole can be fully described by only their mass, charge, and spin, which is resulting in the Kerr-Newman black holes. But when a black hole is perturbed, it rings with characteristic quasi-normal modes that are predicted by GR. And the quasi-normal modes are unique signature of black holes and can be used to infer their properties. But nowadays, the gravitational wave the detection is not very good to detect this quasi-normal modes. But in the future, yes, we can do it. Additionally, when two black holes merge, they undergo a ring down regime that also allow for black hole spectroscopy, which can also provide additional information about their properties. So, what is the black holes? Black holes are very simple object. Black hole are region of space-time with gravity so strong that nothing, even light, cannot escape, and defined by Noether theorem, which I mentioned. Only they have a mass, charge, angular momentum are observable, and there is a boundary which is known as the event horizon, and which nothing can escape. This is known as a null surface, and this black hole, most of them, has a singularity. So this traditional black hole have a singularity at the center with infinite curvature. Of course, there are some regular black hole without singularity also. So this let's discuss how light behave in the curved spacetime around the black hole or compact objects, heavy object, which is essential for the understanding the shadow. So in general relativity, the gravity is the curvature of the spacetime. So light, although massless, follow these curves and leading to the phenomenon like gravitational lensing. And this bending of light is what allow us to detect the presence of black hole indirectly. And you can observe here how much object distort the path of light rays. So this gravitational lensing not only reveal hidden objects but also provide a window into geometry of spacetime itself. So there have only been three revolutions in our way of seeing the universe. So for most of human history, we were limited to naked eye astronomy. In 1610, Galileo used the telescope as a way of gathering more light, and in the 4th century, since telescopes have reached over 10 meters in diameter, in early part of this 20th century, a series of technological advances involving detectors and telescope in space opened new spectroscopy for astronomy, and from the radio waves to the gamma rays. So in 2015, the detection of gravitational waves allow us to see the universe with gravity eyes for the first time instead of this light. So this is very important step. So the 2017 Nobel Prize has been awarded to a 3K player in the development and ultimate success of the Laser Interferometer Gravitational Wave Observatory, LIGO. And after that, another important step is shadow of the black hole. So in 1919, Eddington and Dyson led solar eclipse expedition that measured the deflection of light by the sun's gravity, which providing strong evidence for Einstein's newly formulated GR. And a century later, in 2019, the Event Horizon Telescope collaboration released the first direct image of the black hole, which is specifically the supermassive black hole at the center of the M87 galaxy. But theoretically, this dark silhouette is formed by bending of light near the event horizon, where gravity is so strong, and the photons are either captured or forced into unstable stable orbits. And firstly, Luminet drew it by hand and also one old computers in 1979. After that, Falke in 2000 used modern computers to visualize it and plot it. And today, from the experiment also, we see that there is something like the shadow of the black hole. So, in summary, there are two important things in the shadow of the black hole. One of them is photon sphere, a zone where light circle the black hole in unstable orbit. Another one is the shadow region. This is the dark region we see because black hole gravity prevents the light from reaching us from the behind. So there is very good animation. Imagine you are watching a black hole. But okay, let's see it. Maybe it is slow. even though we can't see the black hole itself, we can observe some fascinating effect it has on light. So here you can see how can you see these light rays and how they are reflected from the black hole and form the black hole shadow. Okay. Uh, and here you can see there's the gravity bends light from the disk around the black hole and giving it the appearance of the halo regardless of the what angle it is viewed from. Some part is bright, other part is looks like a dimmer. Because of that, the radiation from gas and dust moving toward us appear brighter, but on the other hand the radiation from particle moving away appears dimmer, and this imbalance make the ring appear brighter on one side. So oops, if you look at the primary event horizon telescope target, I'm showing on the right here. This is trying to give you a summary of how different black holes might appear if you were to image them with this event horizon telescope. And the idea here is that on the y-axis, I'm showing you the flux of each of this black hole at 1.3 millimeter, which is the wavelength that event horizon telescope observes. And the x-axis is showing you the resolution, at least in the current configuration, will be able to obtain. And the point here is that as you go toward the left on this x-axis, you can get higher and higher resolution, so that the Sagittarius and M87 are very clearly the two best candidates for us to get horizon image. But all of the sources in the purple triangle here at the right upside are that are bright enough for the Event Horizon telescope to observe. So we just won't be able to observe them using this telescope. So one way to increase the sensitivity of the Event Horizon telescope is to capture more energy from black hole target at each Event Horizon telescope. Since black hole emit radiation at many frequencies, we can do this by increasing the range of frequencies that are recorded during the Event Horizon observation. So this requires electronic system and recording system that operate at higher speed. And the most straightforward way to boost the sensitivity of the Event Horizon telescope is to increase the net collecting area of the dishes in the array, but building large reflector is an expensive and sometimes impractical proposition. So especially at this short wavelength, and because the mechanical precision and rigidity of this dish has extremely tight tolerance, which are hard to meet, and an array of telescopes become able to discern finer and finer feature in the emission as the separation between the telescope is increased. So I think that they are going to adding new telescope to the Event Horizon telescope to build an array with a footprint approaching size of the Earth. And also in the future they are going to put a satellite in the space. So theoretically, first the Singer was the first to calculate what we nowadays call shadow of the Schwarz black hole. And after that, for the rotating black holes for Kerr spacetime, Barding did these calculations. Then for the Plebanski and Devensky spacetime, Grenzbach did these calculations. After that, this topic became very uh, hot. So everybody nowadays working on it. So why this the shadow of the black hole is important? The observation of the Event Horizon telescope has provided the first image of the black hole shadow in M87 and also our galactic center Sagittarius A. So if the observations are sufficiently accurate, it can provide us the evidence of the existence of event horizon. So we can test the no-hair theorem GR. We can test the GR itself against number of alternative theories of gravity. and we can also improve some of the gravity theories. Also, we can investigate the alternative of the curved black hole through the relativistic theoretical modeling of the shadow image. If you look at the motivation for gravity beyond Einstein, we know that the GR passed all tests with flying colors. So many classical tests for more than 100 years, and binary pulsar systems studied for half century, then stellar mass compact object with gravitational waves by LIGO Virgo, then supermassive black hole shadow with the Event Horizon telescope. But there are open problems may challenge the GR, like the origin of the dark energy and dark matter, the Hubble tension, and also the quantum gravity in general. So we need more experimental evidence to find the theory behind these problems. There are also some black hole alternatives. So maybe the black hole has some hair. Black hole maybe with this GR include additional fields like electromagnetic charge, not charge, cosmological constant, dark matter halo, hair, and other charges. Maybe we have also black hole solution in nature from alternative theories of gravity or incorporating quantum effects. Also, maybe there are some black hole mimickers or exotic compact objects like black holes without event horizon, with naked singularity, or with wormholes or boson star or gravas star. So only we can check this kind of things using the experiments. Okay. So so now let's look at the theoretical part. So what part of the metric are very really constrained? Sorry. So here, if you look at the formulas, you can see that the radius of the photon orbit depends only on the GTT component of the metric. So the radius of the black hole shadow is just the length photon orbit and also depend on the GTT part of the matrix. So let's look at how we can derive them quickly. This is very standard things. You can see, you can find in every GR books. So photons coming from the black hole, from the source, traverse the space-time of the black hole and get deflected and reach the observer. So as viewed by the observer, we are interested the direction for which no or little radiation is received, and we can use the to study the motion of the particle. We are using the Lagrangian approach to calculate this geodesics. We can calculate the first of all independent quantities t and phi. So you have two constant of motion, which is one of them is related with energy, another one is related with the angular momentum L. And after that, you can write the null geodesic equations for spherical symmetric spacetime. And after that, if when you derive the effective potential, here you can define the new parameter B, which is the impact parameter, which is related to the angular momentum and energy. And by simplicity, if we choose the theta pi over 2 and theta uh, prime becomes 0, then your effective potential become very simple formula. So when you're going to look at the turning point of the photon and calculate its the turning point of photon, then you must check the V effective should be equal to 0 and R dot should be equal to 0. And also you must check the circular point photon orbit should satisfy the first derivative of the V effective equal to 0. So by using these two conditions, you can derive what we said that impact parameter at impact parameter. You can calculate the impact parameter in terms of the photon sphere. And this impact parameter also called the optical radius or shadow radius. but we are at a photon sphere. So this is known as a critical impact parameter. For example, if you do this calculation for the Schwarzschild black hole, it is very simple. 1 minute. We don't have electricity now. It comes, so I'm changing the internet connection. So I connect it from the phone. Let me connect from the yes, yes, I can connect now.
Yes. Oh,
There was
sorry. Yes,
uh,
you.
but okay, because we don't have electricity now. It's come, so I connected from my phone, but now I think it's fine.
No,
Okay,
it's all right. It's all right.
let's
We can see
let's
you again.
continue.
Yeah.
Okay, here the photon enters the black hole system for different impact parameters, and the photon with critical impact parameter ends in a circular motion around the black hole. And this photon is a location where the gravity is so strong that light can travel in circle. So in the Schwarzschild space-time, in order, which is a similar spherical symmetric space-time, and it is also asymptotic flat, the light rays asymptotically approach an unstable photon sphere, and this sphere that is filled with a circular light-like geodesics are unstable with respect to this radial perturbation. In the curved metric, there is no photon sphere, but rather the photon regions. So for Schwarzschild case, when you calculate it, you can see that it is equal to 3m. And if you calculate the critical impact parameter, which is equal to shadow radius, it is equal to 3 square root 3m, which is approximately equal to 5.2 m. So Singh used the escape cone, and also Zeldovich and Novikov calculate the cone of gravitational capture of radiation. But after Barding Chandrasekhar, the apparent shape of black hole is calculated. And then, as I said before, the Illuminate use image and optical appearance photography, and he did using the old computers. And also the observer is very important for the asymptotic space-time, spherical space-time. Yes, you can take it infinity, but if it is not a asymptotically flat space-time, yes, you cannot take it infinity. So if you look at the rotating black holes, the shadow angular size give us information about the black hole mass. And the second thing which we could hope to measure is the oblateness. The oblateness can give us the information about the black hole spin. And also it is important that this deformation of the black hole shadow depend on the viewing angle of observer. And for the equatorial observer, the deformation is strongest, while for the polar observer, the deformation is absent. So this generally speaking, the size and the shape of the shadow depend on the parameter of the black hole. For example, A, this is related to angular spin. And for example, if the shadow become deformed, the black hole is, if it is the black hole is rotating. So this shadow is different than the Schwarzschild case, and this is deformed. When A is increasing, this deformation is increased. And this curved black hole shadows depend only weakly on spin. So here you can see how the shadow change. Here also, this result also cannot place constraint on the parameter in the curved spacetime because there is a they find no noticeable difference for current and non-curve images. There's a 17 percentage constraint, so radius must be between 4.31 m and 6.08 m. So the difference is very small. So by using today Event Horizon Telescope result, it is very difficult to do it. And if you look at the Sagittarius A result, the constraint is 10 percentage, so this radius must be between these values. So firstly, we study the shadow of the black hole, and we study the shadow of the Kerr-Newman-Casio spacetime when I was in the Chile when I'm doing a postdoc. And this Kerr-Newman-Casio black hole is very interesting. It is a charged black hole, but it is a dionic charge, so they are both electric and magnetic charge. So we look at the effect of the magnetic charge on the black hole shadow. And here you can see that when the charge is increasing, the shadow radius is decreasing. And yes, in this animation created by Dimitros Psaltis, you can see the horizon region of the black hole, photon orbit, 3M, and also the photon path, how it deflected. So our understanding of the strong gravity near supermassive compact object has recently improved thanks to the measurement by the Event Horizon Telescope. And they put also some constraint of the black hole charge using the M87 image. For example, here you can see how different charged black holes shadow behave differently. For example, Schwarzschild is uncharged. If you compare with the charged one, Rise, Nordstrom, Bardeen, Hibbert, Frollo, regular black holes, you can see that each of them has a very small differences of the shadow, but most of the cases, charge is decrease the shadow radius. And this 17 percentage error bound can also be used to constrain the charge solution to non-GR field equations. So we can understand if the black hole in the nature, in the Milky Way or other galaxies is charged or not. But if you look at the data from the Sagittarius A, then you can, this data is better, so you can do 10 percentage bond, can place the constraint on the part of the parameters, so that the recently mostly we are going to use Sagittarius A observational data to make constraints. So with Sunny and other collaborators, we also look at the different constraints of gravities using the Sagittarius A observations, and we compare them and maybe more than 50 black holes, and we published it 2 years ago. So this is also very interesting work what we did. So okay, let's continue with the uh, deflection angle via Gauss-Born theorem, and after that we can turn back to the shadow constraint. So Gibbons and Werner, recently Gibbons received the Dirac medal. So Gibbons and Werner present another approach to gravitational lensing theory, which emphasizing global properties, and specifically they consider the astrophysically relevant weak deflection limit, not in the impulse approximation, but treat the light rays as a spatial geodesic of the optical metric, and use the Gauss-Bonnet theorem. And then it turns out that the focusing of the light rays is from this point of view. It is essentially topological effect. So they find surprisingly that this deflection angle can be calculated by integrating the Gaussian curvature of the optical metric, which is related to the Ricci scalar, and out this optical method is outward from the light ray, in contrast to the usual description in terms of the mass enclosed within the impact parameter of the light ray. So it is very simple to calculate the optical metric from the space-time metric, and after you extract this dt part, and you when you take ds square 0 and take the dt to left side, and you can take theta equal pi over 2 in equatorial plane, so you can find the optical metric. So after you find the optical metric, you can calculate the Gaussian curvature k, which is related to Ricci scalar. K is equal to Ricci scalar divided 2. So what is the physically important here? This Gauss-Bonnet theorem or Gauss-Bonnet formula is an important statement about surfaces in differential geometry, and it's connecting their geometries in sense of curvature to their topology with the sense of Euler characteristic. And this Gauss-Bonnet theorem connect the intrinsic differential geometry of surfaces with its topology, and this is very important tool. But here, when you calculate the k for Schwarz spacetime, you can see that it is negative at every point. So this geodesic marks locally diverge. Then you can ask that how can two light rays from a light source refocus at observer, because if it is diverged you cannot observe it, so that these two images of the Schwarz lens obtain it. So there are different geometries like a zero curvature, positive curvature, and negative curvature. So here we find the negative curvature. So then they think that maybe we can use something Gauss-Bonnet theorem to find some relation between the topology, and they use the Gauss-Bonnet theorem for the optical metric, and they come from for the asymptotic flat space-time. They take come from the infinity and calculate the deflection angle alpha. So after they define the optical metric, let's go here. This is your Gauss-Bonnet theorem. You can choose the exterior angle for discontinuity point of boundary. Same theta 1 and theta 2. You can take them pi over 2. Therefore, this Gauss-Bonnet theorem have approximately gives you that this theta is equal to pi, this green one. Then you can choose this region, which the Euler characteristic number for the simply connected region, so that this Euler characteristic is 1, because this is look like a disk. And then this formula, there is also geodesic curvature kappa. This kappa is equal to basically when you go to the asymptotically flat region, it is equal to 1, so that you can take the integral region from 0 to pi plus alpha, so it gives you pi plus alpha. After that, when you substitute inside the Gauss-Bonnet theorem, at the end you will come to this simple equation for the deflection angle. So alpha is related to the minus integral k ds. K is here Gaussian curvature, ds is surface term. So you can apply this Gauss-Bonnet theorem to the asymptotic flat space-time, and you can easily calculate the deflection angle. For example, for the Schwarz space-time, the first term of the Gaussian optical curvature is minus 2 m. Here I write mu, or you can take it m, divided to r cube. And when you substitute inside, the surface theorem will be r dr d phi, and integral you can take it from the R is equal, you can take it from the impact parameter divided to psi phi. This is a straight line approximation to the infinity. So this simple integral gives you 4m divided to b. This is the first term of the uh, deflection angle of the Schwarzschild black hole. What expected? So as you see that this is very simple. So by using this simple theorem, we also wrote many papers. I also wrote this paper in 7 years ago uh, using the Schwarzschild wormholes. Using this Schwarzschild Dammer-Soldikian wormhole, I calculated the deflection angle and then strong deflection angle. So when you calculate the deflection angle by using this theorem, you can see that there's a extra one term. So when this lambda term is increasing, it increases the deflection angle. So I also calculated for the rotating case. A rotating case, it is a bit more difficult because there's a rotation parameter. But this looks like a curve-like theorem. Yes, you can. After that, also I applied this method to the different black holes, like this Einstein-Cartan cable schema gravity. These metrics are more complex, but this method is very simple because instead of using the perturbation method or geodesic method, here you must to find the Gaussian curvature and solve the integral. So after I calculate the Gaussian curvature, I found that the deflection angle in a weak field limit in this up to the second order theorem is calculated like that. So another important thing on this topic is let's go to this one. It is studying the deflection angle in a different medium, because the space is empty, but around the black holes maybe it's not empty. There are some medium like a dark matter halo, or maybe there are some other particles. So deflection angle of the photon in vacuum doesn't depend on the photon frequency or energy. So deflection in vacuum is achromatic, and gravitational lensing in vacuum is achromatic. So this is what we know from Schwarzschild black hole. Deflection angle is 4m divided to b. But how this situation change in the presence of plasma? So in an outer space, the rays of light travel through the plasma. So in plasma, photon undergo a various effect. For a gravitational lensing, the main interest is the change in the angle of deflection angle of the light ray. And due to this dispersion property of plasma, we may expect that the chromatic effect will arise. So the light rays in transparent and inhomogeneous medium propagate along curved trajectories, and this phenomenon is called refraction and is also well known from everyday life. And this bending of light rays due to this refraction is not related to relativity or gravity, and occurs only if the medium is optically non-homogeneous. So non-homogeneous means here that the refractive index depends explicitly on space coordinates. So if you apply this idea to gravitational deflection of light ray in gravity, the refraction index of plasma is in like this formula. Here the frequency of the photon omega is dependent on the spatial coordinate r due to the presence of gravitational field redshift. So we will use the notation that omega infinity is equal to omega. And here the E is the charge of the electron, and M is the electron mass, and omega is the electron plasma frequency, and N0 is a constant, is the electron concentration in homogeneous plasma. This is first done by Pisnovatsky, Kogan, and Tsubko. We have shown they showed that the first time the gravitational deflection in the homogeneous plasma differ from the vacuum deflection angle and depend on the frequency of photon, and so alpha is equal to 4gm divided to b in vacuum. But when you consider the plasma, then the chromatic rotation deflection will be like that. So after that, Krznejko and Gallo used this method in the Gauss-Bonnet theorem and calculated the deflection angle in plasma medium using the Gauss-Bonnet theorem, and we also use this method for different spacetimes. For example, we use it for this Einstein-Cartan-Keeble schema gravity. So this is the index for the cold plasma medium, and which is R dependent, and we calculated the new optical metric, which is also N dependent, and we find the Gaussian curvature for the above optical metric with M parameter. So it is very complicated, but we take only these terms. Then we calculate the deflection angle in weak field approximation. And as you see that when the this plasma medium is increased, the deflection angle is increased. And also with this Li and Zhang, we find a different method. Firstly, we introduce a geometrical approach to study circular orbit of particle in static and spherical symmetric spacetime. But this time, we use the Jacobi metric, and we apply the circular orbit to study weak gravitational deflection angle of null and time-lag particle based on the Gauss-Bonnet theorem. By this way, we obtain a deflection angle in asymptotically flat spacetime, and also we extend it to non-asymptotic spacetimes. Firstly, before us, Isiera et al. In Japan, they extended the Gibbons-Werner method to finite distance sources and receiver for non-asymptotically spacetime. And also Ona et al. Developed the generalized optical metric method for this finite distance deflection. But here, firstly, we use the circular orbit in the finite distance method, and we extend it. So let's see how we did. And we use also, firstly, the Jacobi metric. So here, this is the generic spherical symmetric metric. So, and the Jacobi metric has the E and M parameters. M is the mass of the particle, and E is the energy of the particle. And if you take the mass of the particle is 0 for photon, and E is 1, it becomes the normal optical metric. The energy of the particle at infinity for asymptotic observer is m divided to square root 1 minus v square. Okay, after that, you can go to the equatorial plane, and the Jacobi metric becomes in like that. Then you can calculate the geodesics, the orbit equation of particle moving in an equatorial plane. Here we use u. U is 1 over r, and here the b is impact parameter. If you take v is 1, it again reduced to the orbit equation of light. After that, we also calculated the circular orbit gamma, which is defined r is equal to r co, which is a constant. So here, when you calculate the geodesic curvature of the curve gamma photon sphere, what happens? Kappa is equal to can be calculated using this Christoffel symbol and the metric GRR. And here, if you take the kappa equals 0, the geodesic curvature at this gamma 0 is equal to 0, it gives you that the radius of the circular orbit satisfy these equations. 0 is equal to c. In our metric, c is equal to here r square, and a prime minus a times c prime times this factor, and you can see that this is independent in the metric function b, so you only consider the gtt component and g theta theta. And for a light, you can take v is equal to 1, and you can get the normal photon sphere equation. When you take c is r square, it reduces to this simple form. This is what we know also for the normal geodesics. When you calculate the shadow of the black hole, we always calculate this photon sphere. For example, for the Schwarzschild case, you can calculate the this circular orbit radius with the particle with speed v is like that. So when you take v is equal 1, it reduces to circular orbit of light 3m. So how can we use it to calculate the deflection angle? So basically, this is the finite. This is the how this Ishihara and Otto use the finite distance method. So alpha is related to the Gaussian curvature k and some coordinate angles phi rs. Phi rs is equal to phi r minus phi s. One of them is receiver angle, another one is source. We calculated again this Gaussian curvature of Jacobi metric, and here this part is very simply reduced to this form in terms of the metric components. And you can see that we can ignore the concept of integration here, which has no effect on the study in this paper, so that at the photon sphere, this circular orbit, this part of the integral will be equal to 0. So if you take this part of the integral is 0, you can change the integral limits so that you can take the integral easily. And this time the alpha is directly calculated by this equation. So for example, how can we do it? Let's look at the Schwarzschild-like spacetime in bumblebee gravity. Here the GTT and GRR components are different to each other. There are a very small difference. We calculate the particle circular orbit and we calculate the orbit equation with its iterative solution gives you. Here we go to the higher order terms because there's a v and lambda v terms, v square terms. After that, we solve it for the phi to find the phi s for the source and phi r for the receiver. They are basically same as you see. Only one of them is one of, but there is a very small difference at the second term. Okay, the first terms are same, but in the second term there is a very small difference because there is a relation between the source and receiver, and phi rs is equal to phi r minus phi s, and when you subtract them you can find also what is the phi rs. So after that we can go back to our Gauss-Bonnet theorem, which reduced to this form. Here we substitute inside phi rs and kds term and put the limit to calculate the deflection angle at the finite distance. So after that, what you can do, you can take ur and us as a it was here. You can take ur and us when it go to the 1, it reduce the normal result. But here also you can see the deflection angle in weak field limits. So it doesn't matter if you take the limit from photon sphere to the r, or if you take it from the phi because before that this also and Ishihara they didn't use the photon sphere. Instead of they use the only the phi r and phi s. So we said that instead of using this phi s and phi r for this integral, you can use the photon sphere and r, and you can find the same result, and this one is more easily. And also we make some we study black hole accretion disk for different method using the spherical symmetric configurations with my collaborator Matt, but unfortunately he moved now to different subject. At that time he was last year undergraduate student, but now he started PhD in USA in different subject, more computational things. So we study the deflection angle, black hole shadow, and also accretion disk of the black hole for this nonlinear dynamic black hole to see the effect of the charge P, and we obtain the magnetic charge should be in this range between the 0 and 0.024. So this is very small parameter. And we show that how this small parameter p affect the accretion disk around the black hole. Basically here we use this free falling accretion emission. One of them is Schwarzschild, another one is this nonlinear equidynamic black hole. So, as a summary, we have detected the shadow of the black hole for the first time. The size and shape of this shadow is consistent with the prediction of the Kerr ray. So we can use this observation to constrain the different charges and the mass of the black holes. And as if we did also many work with my collaborators. Also, I work with Adilton Filo in Brazil. So we did many things using the Gauss-Bonnet theorem and also shadow of the black hole. So this is this is very hot topic, and additional telescope maybe will improve the image fidelity and may allow us to measure the shadow asymmetry. And the first image of M87 can be used to measure the radius of the black hole shadow within the 17%, and the image of the Sagittarius A is better within 10%. And these error bars can be used to constrain the modified gravity black holes. And these constraints are about 500 times more stringent than the solar system test, and also comparable to the LIGO Virgo constraints. So future is bright, should be able to perform better tests in the future. So waiting the some data and news from the observations in the near future, there will be a space satellite to detect the shadow of the black holes, so that I think that we can find better constraints. For example, black holes are maybe enveloped in a plasma, and maybe this plasma has a magnetic field areas where magnetic affect how this matter moves, so that as the magnetic field grows stronger, it changes the shape and polarized light we measure for different patterns. Last years, they revealed a breakthrough discovery that this polarized light waves measure that it indicate the M87 has strong magnetic field. And maybe it is better nowadays. It is very important, I think, to see how this magnetic field affect also black hole nature and what is the source of it. Yes, this is very comment. So thank you very much. I think it is a bit long, so I go fast. So thank you very much.
Okay, thank you, Ali. Thank you so much for this beautiful talk. Uh, we have time for questions, so if anyone has any question, can approach here to the notebook. Uma questão, pessoal, vocês podem vir aqui no computador. Okay, so maybe I have one question. You were telling now at the end about this new observational constraints and black holes. So, what do you expect for the next years in terms of advances in this area? What is the, let's say, the most bright advance that you expect to see in the next year about this high resolution measurements on black holes?
Also, yes, I don't know, but maybe in the future we can find something interesting. Maybe we can see that black hole has a hair. We can see something different that us, so that we can guess that there is a different hair. So after that we can search what is this hair. This can be very interesting. Maybe it is interesting to see that because nowadays there are many modified gravity theories, and we have a cosmic tension and this lambda problem, cosmological constant problem. So it is also important to see maybe how this dynamic of the universe affect the black holes, and also how, for example, maybe dark matter and dark energy affect the black holes. So I don't know what we see in the future. But for example, recently I hear that they are planning to send some small nano satellite to the inside the or near to the black holes. Uh, I think it will be interesting. So I don't know when it happens, but maybe we can find something different. So we will see. But
Okay,
if you want to study, I think general relativity and black hole physics or cosmology, in future there will be more jobs and more funding for on this area because there are many satellites and experiments. For theoretical part, yes, it will be maybe more difficult if everything is go same. But for experimental gravity, I think there will be more opportunities. And if they find something interesting, then for for theoretical physicists, we will have more job to do.
okay, thank you very
Thank
much
you
again, Ali.
for
We are
your
with
invitation.
Yeah,
Have a
we
nice
are a bit with a short time here because of the agenda, but thank you so much. It was a
Thank you
pleasure
very
to
much.
have you here with us.
I hope that I will be there next time.
Yeah, sure. We expect you here. Thank you.
Thank you. Bye bye.